I want to do an example of applying our physics problem-solving strategy to a situation with projectile motion. In particular, I've got a story here. Al and Betty are on a hike in the mountains, and Al throws a water bottle up in the air toward Betty, and Betty catches it perfectly horizontally when she catches it. That's our scenario. Al and Betty are separated by 6 meters along the direction of the slope. The angle of this very steep trail is 40 degrees where they're hiking. And what else do we know? I guess the question is, what is the initial velocity of Al's throw? What is that initial velocity Al has to do, magnitude and direction, to be able to make the water bottle come exactly horizontally to Betty? To be clear, I'm going to be talking about the projectile behavior of this, so I don't care exactly how Al does his throw. I'm going to start my story the moment the water bottle leaves Al's hands. Similarly, I don't care how exactly Betty catches the water bottle. All I care about is what happens the moment before she catches it. I want that to be traveling perfectly horizontally at that moment. So I do that so that I don't have to worry about the complicated forces involved and all those things. I just want to worry about the projectile motion part of this, which means it's only the acceleration due to gravity affecting this. I'll go ahead and jot on here, for reference, the acceleration of the water bottle pointing straight down. That's the definition of down on some level, is this direction gravity points, and the acceleration points down in the story. That's what it means to be a projectile motion problem. We're ignoring air resistance, we're ignoring other factors like that. All right, so this is my problem, and to solve this, I'm going to apply our usual problem-solving strategy in physics. And step one of that strategy is always the prepare step. Prepare, that means you draw a picture. I've already drawn the picture, that's good. I draw a picture, but then I'm also going to choose coordinates. Choosing coordinates is part of the prepare step. And for projectile motion problems, we'll understand why to do this later on, but for projectile motion problems, you essentially always want to choose one of your axes to be parallel to the direction of gravity. I'll choose plus y to be upward, and I'll choose the plus x direction to be horizontal. They have to be perpendicular to one another. I want the acceleration due to gravity to be along one of them. I've chosen these positive directions. Any choice is equally valid, but this choice, a choice like this, is a convenient one. It helps the calculation a great deal to make a choice like this, horizontal and vertical, compared to that acceleration due to gravity. And so we've chosen those coordinates. The other thing we're going to do, so coordinates, the other thing we have to do in choosing coordinates is specify the origin of coordinates. Where is x equals 0, y equals 0, time equals 0? And I'm going to set all those things equal to 0 at the moment and position of the ball being, or the water bottle being thrown. At that moment, that initial position of the bottle, that's going to be my 0 point. Again, any choice of 0 point for time or position is fine, but choosing it at the initial point or the final point, something meaningful in your problem, is usually helpful in setting up the equations that you're going to need. Okay, I've done that. I've chosen coordinates. The other thing I want to do as part of my prepare step, I want to make a list of some of the data that we know about this system. So, for example, at this initial point, I'm going to make a list of the motion data. So, initial time, initial x, initial y, initial vx, vx initial, and initial vy. That is my list of motion-related data that I want to know about this point. Similarly, at the final point, where Betty is catching this water bottle, I've got a list of that same kind of data. I've got t final equals x final equals y final equals vx final and vy final. I've got those, that's the data I want to collect. That's the data I want to keep track of to answer all these questions. Now let's think about this. Initial time x and y I just chose to be my origin. So initial time is 0 seconds, x initial is 0 meters, y initial is 0 meters. These things we'll talk about in a minute. Some of these are definitely unknowns. For example, vx initial and vy initial are in fact my big goals for this whole thing. Those are the things I want to solve for to answer my problem. If I can find the x and y components of velocity, I know the full velocity vector. I am set. Over here, Well, the problem hasn't specified the final time. I certainly haven't specified the final x velocity. I have specified the final y velocity because I say it's moving horizontally when it's caught. That means it has no y velocity at the moment that Betty catches this water bottle. X final and y final, they're not directly specified, but I can do a little bit of trig to figure those out, right? If I, let me just for the heck of it, draw a little triangle over on the side. If this is my 6.0 meters, or I'll call it D, keep it simple. If that's the hypotenuse of my triangle, I know my coordinates. I can do components by drawing a line parallel to x from one end, a line parallel to y from the other. So I've got my right triangle there. And then this will be, I guess this is my distance, so this will be my x final, and this will be my y final. Hope you see y, because it's from the initial point over is x and up is y. And so doing that, this is my theta of 40 degrees. If I do basic trigonometry, I know that x is the adjacent side to that angle. So d times the cosine of theta is going to be x, d cosine theta, and d sine theta for my y position initially. I could plug in numbers for those, but I have an aversion to plugging in numbers any earlier than I have to. I know what d is. It's 6 meters. I know what theta is. It's 40 degrees. So those are, it's symbolic, but it's known. Those count as known variables in my mind. All right, that is the setup phase. Oh, the one other thing I should set up is acceleration. Once I know the x and y definitions, once I've chosen coordinates, I can interpret my acceleration. I can see that the acceleration in the x direction is 0, because there's no horizontal component to that acceleration down. And my acceleration in the y direction, I'm going to write that as minus g, because acceleration due to gravity has magnitude g, little g, and it's in the minus y direction. It's pointing opposite the y direction I chose. If I'd chosen y downward, it would be plus g. The plus or minus sign just relates to my coordinates, but the magnitude is definitely g. Now, I finally have all the information I need to make progress, to take the next step in doing the solution. So how do we do that? Well, okay, that was my prepare step. My next step in solving physics problems is always the setup step, where I set up the equations that are relevant for the problem. This is always based on the physics involved, and so in particular, if I look at this, I remember that for two-dimensional motion, the beauty of motion described in vector components is the x motion and the y motion are independent of one another. Those are independent calculations, independent equations. We can keep, because they're orthogonal, because they're perpendicular directions, we don't need to tie them together in complicated ways. I can look and say, my motion in the x direction is 0 acceleration, constant velocity. That's the simplest kind of motion there is. My motion in the y direction is constant acceleration. That's the second simplest kind of motion there is. So this is, I guess if it was just constant velocity in both directions, that would be simpler, but this is the simplest interesting problem we can talk about. So I'm going to have to pay attention to my x behavior and my y behavior and write down some relevant equations. Up here, I've written down the 3 constant acceleration equations that I usually refer to in these problems. There are more or less that you can keep track of. These are, for me, the sweet spot of remembering equations for convenience. More equations gives you more convenience. Fewer equations is less to memorize. For me, the sweet spot is these 3. There's the velocity as a function of time equation, the position as a function of time, and this v squared final equals v squared initial plus a displacement thing. Those are the 3 that I generally try to remember. It's a pretty good spot for balancing convenience and what you have to remember. I've written these down in what I think of as initial and final form. I've written it down in terms of x final equals x initial plus blah, 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 blah. V final equals v initial plus blah, blah, blah. I've written it down in initial final form. A lot of textbooks don't put it in this form. They write it down as just x as a function of time equals x initial plus vx initial times t, and they put t initial there, plus 1/ax t squared. That's fine. I'm writing down the initial final form because in a lot of problem solving, I really am linking together a pair of events by these equations. These equations basically carry you from some initial event to some final event, and they connect those events together mathematically. So that's why I've written it in initial final form. I like writing out initial and final time explicitly because I don't want to assume t initial is 0. A lot of the book equations tend to do that. So this is what I got. So if I apply this to my different directions, I'll start by applying it to the x direction. My ax is 0. So, for example, applying it to the x direction, if ax is 0, I'm just going to plug that in directly because it's quick. I get Vx final equals Vx initial plus 0. Okay, so that's one thing. I link those together. And this one is not going to give me anything new. Vx final squared equals Vx initial squared plus 0. That's less informative than this because it's squared, so it loses the plus or minus sign. Ignore it. And then there's this one that says x final equals x initial plus Vx initial times t final minus t initial. There we go. That's my x equation. That's my pair of x equations. And looking at it, I can already see, looking ahead a moment, that this one, I know that x initial is 0, so I'm going to eventually plug in a 0 here. I know that t initial is 0, based on a choice. I'm going to plug in 0 there. I don't like plugging in numbers early, but I make an exception for 0. Because remember, we got to choose where 0 was. We got to make that choice, and we may as well profit from the choice we made. So I'm willing to plug in the zeros that I chose in order to make my equation simpler. So that's my x equations. That's my x information. What about y? Well, okay, these were written in terms of x up here, but the same equations apply for y if it's in constant acceleration. And so I can do that here. I can write down these 3 equations for constant acceleration. Let me do it for y. It'll take me a second to write it down. I've got Vy final, that's when Betty catches the bottle, equals Vy initial plus Ay times T final minus T initial. I've got Vy final squared equals Vy initial squared plus 2 Ay y final minus y initial. That's that second equation up there. And my third equation, y final equals y initial plus Vy initial times t final minus t initial plus 1/2 Ay times t final minus t initial squared. Okay, that's writing down those 3 equations. I hope you understand that once I recognized y was constant acceleration, I was able to look at these 3 equations and just copy them down with new labels. Final and initial are match these 2 events. The y instead of x, but it's just changing the labels. The 3 equations apply as soon as I knew it was a constant acceleration in that coordinate. And I can simplify again. I can say, what are some of my 0 things? Any of the t, x, and y initial are 0, and Vy final is initial. Vy final is 0, so that's 0, 0, 0, 0, 0, 0, 0. That's most of what I got, I guess. Those are my zeros. And also, when I'm doing projectile motion, I like to see gravity explicitly in there. So I'm going to say minus g for all my AYs. Minus g, and minus g. I'm going to think of those as minus g's. Let me copy all this down in simplified form. Now that I've done all the work to write this stuff down, let me copy it down and simplify once I've plugged in these zeros and the minus g's and see what I get. My list of equations. Okay, I've got my x equations first. I've got Vx final equals Vx initial. I've got x final equals Vx initial times t final. I've got 0 equals Vy initial minus g t final. I've got 0 equals Vy initial squared minus 2g y final. And finally, I've got y final equals 0 plus Vy initial times T final minus 1/2 G T final squared. Long list of things. And one of the things I see students often get mixed up on is keeping track of what are my knowns and what are my unknowns. There's a tendency to want to plug in numbers right away because numbers are obviously knowns. And symbols might be knowns or unknowns. Plugging in numbers gets rid of that confusion. I really want symbolic solutions if you can help it. So to help you with that, one trick that I've seen work for some students is underlining your unknowns. If I go through and underline the two V initials, and underline T final, and underline Vx final as unknowns everywhere they appear, let's do that. Vx final is an unknown. The two Vx initials are unknowns. So, or the two V initials rather are unknowns. Those are unknowns. T final is an unknown. T final is an unknown. Okay, I've got quite a cluster of underlined stuff, but I think everything is not underlined. X and Y final are known. Yeah, okay, that's basically it. A lot of unknowns, lots of unknowns, but we can look at this now, and we can look. We've got a list of equations put together here, and what are our goals? Our goals are to find Vx initial and Vy initial in terms of other things. And when I look at that, Vx initial, this equation is pretty useless because Vx final is also unknown, so I don't care about this one. But when I look at it, this equation here is the only one that has Vx initial in it. So I clearly am going to need to use this x final equals equation to be able to solve for Vx initial. Since that doesn't help, that just adds another unknown. For the other, that means I need to know T final from somewhere. And I also need to know Vy initial. When I look at it, I see three other equations here. Well, finding Vy initial is really easy in this equation, so I'm probably going to want to use this one. That'll find me Vy initial. And given that, it looks like I can also use this equation, which has, if I know Vy initial here, I can use it there to find T final, and it'll help me. I think I've got my set. I've chosen three equations in three unknowns. And since in those three equations, oh wait, no, there is a squared here. I've got something squared. My physics is almost done at this point. I'll probably need to choose a plus or minus sign eventually to figure out something, or at least it's possible I'll need to. We'll see how it goes. I'll have to think about plus or minus signs to make sure I don't mess something up. But the physics is basically done. I've done my setup step. I've written down the relevant equations for each direction, and I've chosen those three equations and three unknowns. So what do I do with this? Well, now's the part where I'm supposed to solve them. Step 3 is solve, and I want to keep this stuff over here for reference, so I'm going to erase my big pile of stuff up top here. Probably I could have done this better, organized this better, but okay. Erasing this so I can take us to step 3, which is the solve step. And the solve step, we already have a bit of a preview about how to do it. Remember, down here, I said this, here's an equation that has one unknown in it. It's nice to have one where we have that leverage, we have one equation and one unknown. I can immediately solve for the initial y velocity. I will see that Vy initial is equal to the square root of 2g y final. And as the square root, anytime I take a square root in a physics problem, I have to remember that's a plus or minus sign implicitly there, because either plus or minus velocity would satisfy that equation. So this is a moment where I should look and say, do I know which one of those is physically reasonable? Is it the plus or the minus that is physically reasonable here? And just looking at this story, I hope it's immediately clear from the story that the positive, the velocity has to be positive to go up to Betty. If it were a negative y velocity, we'd be in big trouble. So positive it is. If I had chosen negative, I think I'd then have to run time backward or something and go to a negative time. But here it is. I choose the positive sign. So there, the physics is done. I've got that set. So next, I can take that and plug it in. I've no Vy initial. I can plug it in over here and say, well, I'll solve for T final here in this second equation. What do I do? I'll add here. I'll say that T final is equal to Vy initial over G. If you see where I got that, added this to both sides, then divided by G to get T final by itself. And I know what Vy initial is now. It's equal to this thing, the positive square root of 2G Y final. So that's equal to the square root of 2G Y final over G. Or I guess I can write that as the square root of 2Y final divided by G, using a little simplification inside of a square root sign. So I've got that. So now I've got an equation for T final. Knowing T final, I can finally solve for Vx initial. And let's see what that looks like. Just divide both sides here. That tells me that Vx initial is equal to x final divided by T final, because it's constant velocity. That actually looks like change in position over change in time. So this is comforting that that's what I end up with. And that means x final divided by this, that's x final divided by the square root of 2y final over g, or I can rearrange this in a bunch of ways. I could write this as x final times the square root of g over 2y final, or I could even write it as the square root of g x final squared over 2y final. However I want to write it, I've got that written down now. I've got an answer. And we can look at this. That means my goal was to find Vx initial and Vy initial. And look, I've got Vx initial and Vy initial written down here. I haven't plugged in terms of d cosine and d sine theta yet. So I guess that's my next step. I've used these. I can make myself some room. All right. So plugging in terms of those variables, what do I find? I guess my y final was d sine theta, so I'll do x first. Vx initial equals, I'm going to do that all under the square root sign thing in hopes that some things will cancel out. Let's see. The square root of g times x final squared is d squared cosine squared theta divided by 2 times d sine theta. That simplifies a little bit. The d squared cancels a little. And cosine over sine, do I really want to do some simplification like that? I don't know that it helps much. Yeah, it's not going to help much. I think I'll just write this as g times d times cosine squared theta over 2 sine theta, all under a square root sign. That's my Vx initial. And my Vy initial is up here, the square root of 2g d sine theta, because that y final was d sine theta. So I've got that, and at this point, I can actually plug in numbers. I can plug in my numbers. This top one becomes 9. Oh, I should put this. I didn't leave enough space. Brilliant. This top one becomes the square root of 9.80 meters per second squared times d was 6.0 meters times the cosine squared of 40 degrees over 2 times the sine of 40 degrees. And when I plug in numbers for that, I earlier got 5.2 meters per second. I could at least check the units. Meters per second squared times meters is meters squared per second squared. Square root of that is meters per second, so that's good. And down here, this one is the square root of 2 times 9.8 meters per second squared times 6 meters times the sine of 40 degrees, all under that square root sign. And that comes out to be approximately 8.7 meters per second. So I now know the components of my initial velocity. And that is, if I asked what was the initial velocity, knowing both the x and the y components is enough to have answered the problem. So I can say right now that I know the components of initial velocity. It's more up than sideways, about 50% more up than sideways, so steeper than 45 degrees, maybe here or something. That's actually not bad for what I've drawn in my rough sketch, so I feel pretty good about that answer. It seems reasonable. The units check out. Right. I'm already moving on to step 4 of our strategy, by the way. You can see that it's instinctive by this point for me. Step 4 for any physics problem is to assess your answer. My units worked. I did that along the way because it's instinct. The direction of my vector is reasonable for the story. The magnitude, the speed is reasonable. 10 meters per second or something is plausible. It may not be. It may not. I don't know if that's too fast to be reasonable or not. But it's certainly not 8,000 meters per second. That would be weird. And it's certainly not 8 millimeters per second, which would be weird. It's in the ballpark of something that I think is plausible. So I like this, and you could do all sorts of other calculations. If you want to know how long this took, for example, you could do 2 times y final over g to find out that this comes out to be whatever, 2 times, what. You can work out that it takes about 1 second to get there. There are a lot of double checks you could do, but that gives you the idea of how this works. I found those answers. If you wanted to, you could also work out the angle the angle of the initial in terms of degrees or something. You could work out the magnitude as meters per second using the Pythagorean theorem. But those are all extra steps. I've figured out what my x and y components are for that initial velocity vector. I've solved the problem. And I guess maybe just to reassess what we've done, by using our problem-solving strategy, I was able to get through this without having to be tremendously creative about how to solve the problem. All I had to do was draw the picture, keep in mind what the 2 interesting events were, the throwing event and the catching event. Those are my interesting events. I wrote down the standard motion data for x and y for each one of the 2 events. I kept track of which thing was constant velocity, constant acceleration. Fortunately, I didn't have any variable acceleration things in this, or it would have been more complicated. And once I did that, the rest of the problem consisted largely of sort of turning mathematical cranks. Constant velocity, plug in the numbers into the standard equations for that. Constant acceleration, plug in the numbers, well, plug in the knowns and unknowns at least, into the standard equations for constant velocity, constant acceleration, and then just sort of plug through, find 3 equations and 3 unknowns in this case, and then solve. And I was able to find those answers in a relatively straightforward way. The creativity, the physics, the work came in setting it up carefully, thinking about what the events were, thinking about the fact that it's a known Vy equals 0 at the end, thinking about what those knowns and unknowns were, and recognizing what was constant velocity and constant acceleration so that I knew which mathematical models would apply to link those events together. That's what there is to it, and I hope that gives you a better sense of how to use our physics problem-solving strategy for projectile motion problems, or really any constant velocity acceleration problems you might run into.